Alright, I decided to do a video on the range formula because a couple of you have asked about it, which is really cool. I mean, it is one of, it's a great example of how simple and elegant math relationships can be. So, particularly for this situation where you just need to find the range, you have the initial velocity in terms of magnitude and the direction, makes this really simple to calculate. In a situation where you don't need to find the time, you don't need to find anything else except for the range, you can jump straight to this lovely looking formula. Honestly, we hadn't gotten to this because I had saved this for the next section, where you do need to solve for the angle if you are trying to reach a certain range, and also because we hadn't gone over where this comes from. And I like you guys to know where things come from, because it's one thing to know how to use it in the future, or you might already notice that in the world, those who understand how that works, you'll tend to be in charge of other folks who know how to use things, but might not know why something works, and therefore when to use it. Yeah, in our smart economy, computers will tend to take over a lot of the processing of steps, whereas people will always be needed to make the judgment calls. Regardless, I think this is a great one to go over, because I also realized, these equations also just come from these first two, if you remember how we came up with these. So in a sense, if you know these first two, everything else is algebra and substituting and solving, and so in that sense you really don't even need these. These are also just simplifications that you can jump to. For example, if you don't have time, the variable, or the value of the variable t at least, and here if you don't know the final velocity. But otherwise, these two are actually all you need to know to find everything else. Okay, enough of that. So where does this come from? Well, it actually comes from, so here is our initial velocity at an angle theta, and we're looking for the range, I'll call that displacement, in the x direction. So remember, by definition, we said that this is the cosine value of v naught times time. So this horizontal component of our velocity, and I'll draw in our sine component as well. So there's v naught cosine theta and v naught sine theta. So that's my horizontal velocity times time. That's going to be the distance, right? Rate times time is distance. Okay, well, this we can calculate as long as we know our initial velocity. Now the time goes back to, and this is, I know something that we're all working on, time goes back to how long does it take gravity to reduce that initial vertical velocity, v naught sine theta, to 0. How many seconds? How many seconds of 9.8 meters per second acceleration does it take to reduce my initial vertical velocity to 0? That will be at the top. And then we're going to double that to reach the full amount of time where my projectile returns to the ground, right? Which is how we define range. So our time really is 2 initial vertical velocity divided by gravity. Okay. So that's what we needed to go over anyway when it came to solving for time, and of course using that, solving for maximum height, etc., etc. So it's the same thing that we've been doing. Only now if we take this and substitute it in for t, then we have range equals, I'll put the 2 out here, v naught cosine theta, v naught sine theta over g. Right, so there's v naught cosine theta, there's my 2 v naught sine theta over g, which comes from my time. Alright, so we will take our v naughts and put those together. So our range is equal to 2 v naught squared cosine theta sine theta over g. And you could leave this as that when it comes to a range formula. There is a trig identity that makes this easier that I won't do here, but cosine theta sine theta times 2 is actually equivalent to sine of twice theta. Really interesting trigonometry identity, and very useful because 2 cosine theta sine theta is exactly what we ended up with in this range equation. And so, to make things easier, we can actually replace 2 cosine theta sine theta with sine 2 theta. And then our range becomes v naught squared sine 2 theta over gravity. Alright, so that formula right there. Alright, now turning it into sine 2 theta is not just easier, it's actually necessary if we, for example, have a range. Let's say we want to go 100 meters. And we know our magnitude. For example, say it's some launcher, and we happen to know how fast it can launch objects, and we just need to know, okay, well, what angle should we point that launcher at in order to reach exactly, say it's our target 100 meters away. Well, I can use the inverse sine to figure out what 2 theta is. Right? I can't do the same thing when I have a cosine theta, sine theta, because those are going to be different, and that's more. It's kind of like having 2 variables. It's hard to nail down what that is, and so when we're solving for the angle in the kind of our next subunit, we're going to need this formula in order to do that. And so looking ahead, instead of having our velocity and figuring out range and height and time, we're going to go the other direction, which is, hey, if we want a certain range, if we want a certain height or time, then what initial launching velocity do we need to have? So stay tuned for that. But that's where the range formula comes from. And so if you want to remember that, you certainly may use that. Otherwise, knowing how to do this will suffice. So you've got options. You can either memorize some beautiful formulas, or you can know the process by which those things come.